So hi, the plan today is to take a look at part 2 of our series in power sensors and meters, and we're going to look at this HP 8484A, which is a minus 70 to minus 20 dB power sensor. It's a second-hand sensor, pretty old, it's an old serial number. It seems to generally work okay. But I want to have a little look at the chopper performance in particular, using the modification that we did to the power meter in the last episode. So we'll run it through some basic tests, see how it performs, then we'll get it on the new equipment and see how the chopper within this is actually working. That'll be quite revealing, and then hopefully we can tune it up. Okay, I've connected the sensor up to the power meter using a 30 dB attenuator. And I'm just going to, after I adjust the contrast a bit, I'm going to set the calibration factor to 100. It should be 99.99, but 100 is the closest I can get to that. And we can see we've got a nice 30 dB reading there. What I'm going to do now is I'm going to disconnect this and connect it up to an external signal generator and just see how far off things are. Now the signal generator isn't perfect, it's probably within about a dB, and the attenuator isn't quite 30 dBs, it's 29.6 or something like that, but it'll give us a good indication as to how things are going. Okay, I've set up the signal generator, outputting 50 or minus 50 dBs, so that's round about what I'm expecting. I'm going to make a few changes now to the output level, see how that behaves, and I'll go hunting for the lowest level that I can distinguish and get reasonable values for. So this is supposed to be minus 60, so we're getting a bit of drift away from ideal here, but it could be the generator, not just the meter. Minus 65, and the error has increased a little bit. Now I'm hunting around to see if I can take it down to minus 75, things like that. It just won't go anywhere at all, and I'm going to try and go the other way and see what a higher reading like minus 20 dB will do instead. Okay, so there you go, minus 21. The generator is actually outputting plus 10, and at that sort of higher end, actually the generator is a little bit suspect. So I'm generally happy with this reading. Okay, so I think we've seen enough of that. What I'm going to look at now is the chopper error. So these are the two halves of the signal coming out, and so this is the high gain output from the modification that we made, and the scope is set up per the instructions. So essentially 50 millivolts per division. We are looking for the difference between the two parts of the chop to be less than 50 millivolts really, ideally much better. And on this trace we can see two halves of the chop, and we can also see some pretty nasty spikes above and below going off the edge of the screen, but we can measure those later. Okay, turning on the actual chopper so we can actually just see that in sync. And the chopper is used as the trigger so that the image from the amplifier stays nice and stable. You can see the big problem here is the amount of noise coming through. Now this is set with 0 volts going into the actual sensor. So this is our 0 value. And essentially the difference between the two voltages on the chops, one is slightly above 0, one is slightly below 0, that gives us the value that's displayed on the meter. So essentially it's saying with 0 input I'm going to get a value on the meter, and we know because we looked at it, it's about minus 68 dBs, and this can't go any better than that. So we can never get to the minus 70 that it's intended to reach. If we put a higher signal in, then the upper and lower differences would increase in scale with that. So I'm just going to try and fine tune the cursors to get them in the middle of those noise areas. Okay, so we've got plus 21 and the bottom one I think is, yeah, it's not bad at minus 25. So ideally it could do with being a bit better. With 0 volts in, this should actually be a kind of straight line, a straight noisy line, straight along the 0 line in the center of the scope. So the modification is working well. It is working as a means to measure the lack of balance within the balanced chopper in the sensor. I'm just increasing the averaging so that we can get rid of a little bit of that noise. Yeah, and that I think shows that we've got the cursors in around about the right place. It also shows the non-linearity of one half of the chop. There's a bit of a curve on it. Ideally, we'd like that curve not to be there. It really depends, of course, where the meter is sampling this to display its values. Okay, time to look at the spikes in a bit more detail. So just taking a moment because of the averaging. And I've got this set on 500 millivolts per division, which does make those spikes quite large, in fact. Sorry about that, just accidentally moving the position of the trace instead of the cursors. Okay, so there we go. We've got about plus 860 millivolts and a minus 1.15. So let's call that 2 volts peak to peak. We really want that to be under about 500 millivolts. That figure is from the 8484 manual, where it specifies that that's what they calibrate it to in the factory. When we open up the sensor, we'll be able to adjust this live, monitoring the effect of any adjustments that we make just by wiggling a few wires. Okay, time to take the sensor apart. So first thing, I suppose, the label. This is supposed to be a table of frequencies versus calibration adjustment levels. I had to look at it under a microscope in order to read it, and I've made some new labels ready for when it's finished. So first step is, let's take out this connector, or the screw for the connector at least. I'll link in the part numbers for these connectors below. They're Molex. You can get Molex connectors that will do the job. Screws are a normal posi drive. Okay, and the same screws on the other end for this large flange. And very disappointing inside. We've got a nicely machined outer casing and yet another shield on the inside. So the inner screening does split top and bottom, but in order to do so we've got to take these end flanges off again, and for that we're going to need some precision screwdrivers because these are small, I think 1.3mm hex heads. Okay, so just trying a couple of the bits in, yep, and let's get those little screws undone. Okay, so the 4 on this end, pretty straightforward, if a little fiddly. Okay, last screw. So that's that. This end flange and the socket are now loose, but it still won't separate because it has some screws in the other end. Okay, so we need to unscrew that flange, but we won't be able to get our screwdriver in there because there's another larger flange in the way. Once that little flange is off, then we'll be able to separate out the screen. So first job is to take the end connector off the end, and it's a little bit tight. So I'm going to have to just nip into the garage, pop in the vise, just that big flange area, because I don't want to hold the body and turn the end connector. So I need to hold that flange and then I'll be able to just unscrew the end connector without any problem. So we're back from the garage, the end connector is removed, and here it is, and still the flange won't come off, but the end connector's off, and we can see an interesting design, which is the solid pin from the end connector is extended, and that presses against a little pressure pad, a spring-loaded pad on the inside where the diode sensor is. So literally put it in and it just pushes up against it. So I'm keeping that clean and out of the way. So this flange is held on with two very, very tiny hex heads, and I'm not 100% sure of the size. Yep, there we go. So these are 0.9 millimeters. Okay, and we can see now that I've clearly got enough space to get in there to undo the 4 screws that I wanted to undo. So I can take that flange off and get the shield apart and get at the circuit board. It's a little awkward. I could just actually do with a flexible driver extension on this. I do have one somewhere, but it's easy enough. I'm not going to bother. These screws are considerably longer than the ones in the other end. Okay, so that's them all out, and whoop, there we go, and the top falls off. So I'm going to just go in with a close-up on this, and I'll take it still, and we'll just have a look at a few things on the circuit. So slightly interesting, of course, that none of it's surface mount. It's very unusual nowadays. I'll try and get a paintbrush or something so I can mark a few things. So just here we've got the FET balanced chopper. So this is what we're really interested in, and up front the diode sensor is buried beneath all this screening. We've got 2 gold wires that come out of it, go through this little plastic holder which holds a couple of ferrite beads, and then the gold wires come over and touch on 2 pads on top of the shielded balanced chopper, and are pressed down by this piece of plastic. And that's it. That's how that entire front assembly is attached. There's no solder, nothing like that. So the gold etc. is used and balanced so that we don't have any voltage differentials from thermocouple effects going on. Okay, now we're interested in the chopper wires that are going across to this. And the instruction manual says to do the balancing, what we have to do is move 2 wires around, and they're connected to G and H on the socket. Now it's these 2 wires just here. So this is brown on white and black on white, and essentially the balance, moving these around will change the capacitance and change the balance of the balanced FET chopper. So the difference between the high and the low should get closer to 0 volts, and the spikes should be reducible. Of course, if we go the wrong way, they'll increase. Working across, we've just got our passives, we've got a few tantalums, So this one decouples the signal. So we've got DC coming into the chopper, we've got AC coming out through a capacitor and into the first stage amplifier, and this just here is the transistor. It's made by Motorola. I was hoping that we might see a part number on there, but unfortunately it's the HP brand part number, which is 0610, and there's no equivalent for that marked in even the HP lookup tables. The other wire that's of some interest is this one down here. Let's change colour, I think, for that. Thank you. Is this one down here, which is black and yellow on white, and that's the output, or an output. And this one over here, similarly interesting. Moving those around may also adjust the balance a little bit, but not as strongly as the brown and white and the black and white. So I've got the open sensor plugged in again, and as you can see, looking at the spikes, nothing's really changed since the original tests that I did. And now I'm just going to start tweaking that brown and black wire to see if I can actually affect a little bit of change. Okay, wrong way maybe. And I'm pushing on the brown wire and really sort of deforming that down towards the board a little bit, and as you can see, that's actually making quite a significant difference to the spikes. At this sort of scale I can't really see what it's doing to the voltage difference between the two halves of the chop, but certainly making a big difference to those spikes. So taking a look at that chopper difference now, and that is significantly better, I think. We just need to zoom in a bit more. And I'm just measuring up these spikes again. Yeah, so 432 millivolts now. That's a lot better than it was. And minus 624. So we've still got about a volt peak to peak, which is about twice what I would like. But it's considerably better than what we had before. Now, I'm going to just stop this for a second, because what I need to do is reattach the bulkheads back onto half of the screening, because as I'm doing this I'm realizing the socket itself is flapping around in the breeze, and that just needs to be stable, otherwise I'll do all the adjustments and I'll reassemble it and it'll be wrong again. So I just need to do that. Okay, I've reattached it, but another calamity has occurred now, which is that the brown and white wire has snapped off from the connector. So I'm just going to look where I need to put it back on again, and it's going to go on G, and fortunately that is in an accessible position on the outside ring of connector pins, so I should be able to get in there to strip it and solder it. So I've stripped the end to about 3 or 4 millimeters. I'm just going to tin that fairly well, because it's very difficult to get my iron in here. Bit of extra solder on the connector, and just reaching for a pair of tweezers so that I can maneuver things around. And I'm going to just kind of stretch out this wire a little bit so that it reaches, and I've used the original wire. I, don't want to change the characteristics any more than I have to. It's very hard to see, get in here and solder this. I'm a little concerned that there is another pin really close, and that I may in fact have got a short circuit. So I'm just using a scalpel to run between those 2 points, just to make sure that any little flashes of wire are pulled out. That's done. Okay, excellent. Okay, back on the meter, and we can see what a disaster that's made of things, really. Obviously that cable is severely disturbed now, and our spikes are very, very bad. We're still on 200 millivolts per division, and they're right off the screen. So we're going to have to do quite a bit of work to get these to behave themselves. And really it's a case of going in there now and just slightly deforming these wires, just gently pushing them. So I'm just gently pushing the wires using some ceramic trimmer tools, just trying to get a sort of optimal position. I mean, you can see just how much these things change. Now, obviously, I want to keep also the main signal through the centre to be a fairly flat line as well. So it's all a little bit of a compromise. As you can see, I'm generally moving these spikes up and down, not actually changing their sizes at the moment. I would like to end up with roughly 500, 600 millivolts peak to peak on the spikes. Now this is going to take a little while, making very small adjustments, trying to get the spikes right. And then of course I'm going to have to go in close and look at the other figures, other slopes as well. Now I'm about 600 millivolts here, so I'm probably going to focus now on, instead of on the spikes, I'm going to focus on minor changes that I might make to the balance itself between the flat parts of the signal. Now this isn't great because I've got too much slope going on, so the difference in signal looks pretty good across the middle between the two chops, but because the right hand one drops a lot, there's still a lot of AC going through to the next stage. So it's going to require quite a lot of tweaking to try and flatten this out. Now, although this doesn't look too great, we are beginning to approach the point where the majority of this centre of the two chop signals is actually pretty much flat. There's a little bit of a switching point where it goes a bit further out, and we can lower that down a little bit, but we're actually now within about 40 millivolts or so, and probably on the point where the meter samples we're down into the 20 or 30 millivolt difference. So pretty happy with that. What I'm actually going to do now is switch to putting real signals into it, because this is of course zero signal. There we go. So here's some real signal going in. Just taking it off the edge, I'll need to rescale that. But we can of course just see whether or not we are able to distinguish smaller signals. Now there's not a huge amount to see on the scope as I do all of this, just tweaking the wires just a little fraction, just trying to get the best compromise to be able to read off the small signals. So I'm not really going to show any more of that. I'll stop it here and we'll move on to reassembly. I suppose the spoiler is, yeah, we got down to about minus 69 dB, not quite to the minus 70, but that was pretty good. It certainly extended the range quite a few dBs. Reassembly, of course, is pretty much the reverse of taking it apart. I would suggest that once you've got the main screening together, that you put it inside the outer casing, attach the flanges to the outer casing before doing things like the small grub screws to hold the flanges in place. And then of course just any tightening up that you need to do, such as attaching labels and that sort of thing. Clearly you didn't want to sit here watching for 13 minutes as I carefully reassembled everything. Okay, so there it is. We've used our modified power meter to measure the chopper error and the spikes that are occurring during the chopping. We've seen how to take the sensor apart. We've seen the wires that need to be tweaked in order to adjust those spikes and to adjust the balance. And it's amazing just how much that balance can be moved around. So that's it. Hopefully you enjoyed having a look inside a power sensor. and how to make adjustments to it. If you did, please click on the thumbs up button, the like button, and also subscribe. And we'll be posting the rest of this series fairly soon. And of course, we'll be looking at building a calibrator next, and then we'll be repairing a power meter or two using that. So, hope you enjoyed it. Take care. See you next time.